Now that we've laid the groundwork for the use of phase lines, not only are they simple for autonomous models and remove extra axes, but I also want to put this out there that a lot of times when you do analyses, you try to make the analysis as simple as possible. So whenever you can, omitting an axis reduces the complexity of the information. When we are able to summarize what's going on in a model just based on one axis without having to draw time and say, you know, for all time in the model, dy dt equals 1 minus y. If y is ever above 1, for all time it will decrease until it reaches y equals 1 as its equilibrium point. So having the t-axis in here is not necessary for me to understand. The other advantage of working with phase lines is that we can go back to studying models with parameters in there. So let's say we have some general model. This model is what we call the logistic differential equation, and it's a little bit more realistic than, say, something like dy dt equals 0.1y, because in this model, this solution will always be exponential. It will be of the form ke to the 0.1t. And if you plot that, as long as your population starts off positive, we're arguing that the population will continue to grow unchecked, unbounded, forever and ever and ever and ever. This logistic model, however, is one that limits the population growth. So what we're going to observe in this one is that the population starts off growing exponentially, but then as resources run out, as food supplies run out, as disease begins and competition begins within the species, you actually start to see some leveling of the population. So whereas the exponential model, this one, will indicate forever growth, the logistic model will start to flatten the curve. And we've heard that in society recently quite a bit about flattening curves. All right, so with this model, we think about k as the growth rate parameter. And in this case, we're just going to say it's k equals 0.1, so we get to substitute out a value for k. And c is what we call the carrying capacity. And you'll see why in just a moment, what that means exactly, if you're not familiar with that phrasing. But in our model, you see that we have this parameter in here. And just recall that a parameter is constant for any given scenario. But maybe what we want to do is we want to study how changing that carrying capacity is going to affect our phase line. So how it's going to affect different populations. All right, let's go ahead and execute an analysis of that parameter. So rather than having to solve this, which we could do, and then we could go to Desmos and play around with the value of c, which will inevitably be part of our solution, we could do a simpler analysis and just generate some phase lines and understand how the solution will respond to different values of c. Consider the integer values on the interval c between 1 and 4. Create side-by-side phase lines for these 4 values and describe what effect c has on the phase lines. So let's start off by doing an analysis for c equals 1. So if c equals 1, that means, and I'm going to draw my phase line right above here. So if c equals 1, I'm going to be looking at equilibrium points of 0.1y times 1 minus y over 1. Okay, so to find the equilibrium points, there are a couple of ways you can do this. This one's factorable, but if you wanted to find the equilibrium points, one thing you could also do is graph the differential equation and look at the intersection points or the zeros of that function. So let me go ahead and do that in Desmos real quick. So here I'm going to go ahead and just plot 0.1, and I can't do y, so my x-axis I'll kind of just think about as the y-axis, 1 minus y, x over 1. And if I really zoom in here, I can see that this is my dy dt axis. So this function here is the derivative. This is dy dt. And my x-axis is actually a measurement of y. So we see that when dy dt is in this interval here, between 0 and 1, we see that dy dt is positive. All these values here on this curve are positive values of the vertical axis. If y becomes less than 0, you have negative values. That means y is decreasing. And if you have values of y bigger than 1, we see that all the values on the dy dt axis are negative. So here I can snap to these, and I see that there are 2 points. When y is 0, dy dt is 0. And when y is 1, dy dt is 0. So those are my 2 equilibrium points. This graph clearly allows me to see already that if y is less than 0, I'm going to draw a downward arrow. If y is between 0 and 1, I'm going to draw an upward arrow. And if y is bigger than 1, I'm going to draw a downward arrow. So here we go. Let's draw that phase line. And we said that one of the equilibrium points is y equals 0. The other one is y equals 1. And so we said that in between here we have growth. The population is going to be increasing. Try this a better way here. Let's go with green. And if y is bigger than 1 or less than 0, the population is going to be decreasing. So what we really meant by carrying capacity is that's the most the population can hold. If y becomes bigger than 1, then the population starts to die off and tries to die off back to y equals 1. So we have a sink at y equals 1. That population wants to reach its carrying capacity. It cannot carry more than its capacity. It's like a room capacity. And here we have a source. That's a very unstable equilibrium point, but that's okay. We can't really have populations that are negative anyway. We're just drawing this for completion's sake. Now we'll do the same thing for c equals 2. For c equals 2, the only thing that will change is in our equation here as our carrying capacity value will become 2. And notice that what happened is our equilibrium point, one of them moved from y equals 1 to y equals 2. So if I actually begin another phase line here, I'll still have an equilibrium point at y equals 0. But now my other one jumped to y equals 2. And we saw that that didn't change the behavior on the inner interval. The population still wants to tend to its carrying capacity, but anything above the carrying capacity causes the population to die off a little bit. Again, competition, resources, hunting, increases in hunting, etc. to keep the population at bay. For c equals 3, you guessed it, we're going to have an equilibrium point 1 at y equals 0, and now 1 at y equals 3. And so what will happen, again, we could graph this and verify, but you'll have populations that want to tend to the carrying capacity, and then of course this meaningless 1 down here. And then for c equals 4, same process. But now I'll have one way up here at y equals 4 and down here at y equals 0. Population will want to increase if y is between 0 and 4 until it reaches its equilibrium. It will want to decrease if we exceed the carrying capacity of the species. And one of the things that we could see is that these carrying capacities, 1, 2, 3, 4, if the population size is in hundreds or thousands or millions, then you could have values between c equals 1 and c equals 2. So we actually could continue to draw phase lines. We just limited ourselves to these 4 values, but we did a pretty powerful analysis here. We just really learned what that value of c does. The value of c just creates a bigger gap between our equilibrium points, 1. What that practically means is there's a larger interval for growth if you have a higher carrying capacity. And what that also means is that in all 4 instances, the population behaves in the same way between the intervals. And notice that the classification of our equilibrium points is still sink, source, sink, source, sink, source. And again, the last one is y equals 4 is a sink and y equals 0 is a source. So here's our analysis or the conclusions of it. If the population is between y equals 0 and y equals c, this analysis of drawing these four phase lines revealed that the population will increase towards its carrying capacity. The second thing we observed is that larger values of c result in larger windows of growth between y equals 0 and y equals c. And thirdly, the nature of the two equilibrium points never changes regardless of the value of c. Y equals 0 is a source and y equals c is a sink. Beautiful. So having these phase lines side by side was very convenient because we could see how small changes in the parameter affected the long run behavior of the solution depending on where your starting value of y is. Also, again, one other thing we could point out here is if we wanted to superimpose the t-axis, I'll just do this kind of real briefly here, but here if we had the t-axis, if y equals 0, then y equals 0 always. If y equals 4, then y will stay at 4 always. And if you're between these intervals, if you started really close to y equals 0, as we'll see later on, the solution would start to increase exponentially. But then once it reached the midway point, there would be an inflection point here, and the rate of change of the function would start to decrease. And you'd have a concave down segment. So populations would increase in this sort of shape in between here. And we could solve this differential equation and prove that. And if populations started up here, they would exponentially decrease. So these equilibrium points are not just values of y for which dy dt is 0 and the population doesn't change, but they also act as asymptotes, which is pretty interesting. So the last thing we should notice is that the number of equilibrium points did not change, and neither did the behavior in the intervals surrounding them. We say that varying the parameter c does not result in a bifurcation. A bifurcation point is any value of the parameter such that either the number of equilibrium points changes or the behavior in the interval surrounding them changes. Often, however, a bifurcation occurs when there is a sudden change in the number of equilibrium points, which then necessarily changes the behavior and intervals surrounding them. The drawing of a phase line side by side, as we have done, is referred to as a bifurcation diagram. So what you might see in situations like this, a real bifurcation plot in the sciences, is you'll see actually people superimpose and try to connect the dots here. So they'll basically draw a line connecting the equilibrium points here, and then they'll try to draw a curve or a line connecting the equilibrium points here. And so what that does is it just really visually divides the intervals. And so if you had a phase line, say here, that would necessarily kind of complete the graph. So we're kind of turning these one-dimensional phase lines into this two-dimensional drawing, where the second dimension, if you notice, this is now our c-axis, and this is our y-axis. So we're looking at what happens to y as a function of what happens to c.